This video is activity 1.2.5 for aerospace engineering, aerodynamic forces, talking about drag. So the drag equation, C sub D would be how we would label or talk about our coefficient of drag. And so if we have a wing going through the air, we're going to have some air sticking to that wing and creating drag. And so again, this is determined experimentally, and there's other factors that come into play, such as the shape and the angle of attack, just like the coefficient of lift. And here you can see all the different values that we have associated with um, our formula. And so here is our coefficient of drag equation. And so C sub D is our coefficient of drag. Our drag is in newtons. Wing area is the same as before. Density, velocity, and dynamic pressure, all the same as the coefficient of lift. So uh, an object does really affect your coefficient of drag. So here you can see that we've got a flat plate, and they're telling us that the coefficient of drag is pretty high, 1.28, whereas like a bullet is 0.295, or this airfoil right here has a 0.045. And all the objects have the same frontal area. So that whole area on all of these is going to be equal. And so you can see how the shape of all of these different profiles actually do affect how it flows through the air. So let's actually look at an example again here. So we're going to take the same Cessna, applying in the same conditions. It's asking us to calculate the drag that is produced when the wing is configured such that the coefficient of drag is 0.05. So let's actually look at our problem here. So the coefficient of drag, we said, is 2d over APV squared, okay? And so we said that d is equal to the amount of weight that we need to drag. Our coefficient of drag is 0.05. So coefficient of drag and drag are two different things, okay? So we have to rearrange that problem so that we can calculate our drag. And so when we rearrange it, it's C sub D over A PV squared over 2. And so now I'm just going to simply plug in all of my values. And when I plug in all of my values, I'm going to get 436 newtons. So here you can see that we don't really know what D is, what the weight is that we have to kind of overcome here. We know our velocity, which is 28.3. We know that our air pressure is 1.196. And then we had our area of our wing, which is 18.2. So again, that's kind of how we factor out this problem to get our answer of 436 newtons. One of the things associated with drag is downwash and wingtip vortices. So there's a pressure difference at the wingtips, and air has a tendency to spill over the wingtip perpendicular to the main airflow. So here we get this additional air that's kind of swooping around on the end of the wings, and it's actually creating more drag and slowing that plane down. Um, and so airflow flows both upward and rearward, forming a vortex. And so this decreases lift, and it also decreases lift and also affects our drag. It increases our drag, and it also would affect our fuel efficiency as well. If we got something pulling us back, that would actually slow us down. So here's an example of what that may look like, where you can see these vortices creating these swirls behind this jet that's flying through all these clouds. But one thing that kind of counters this is something called winglets. And so they're vertical airfoils that limit vortices and improve fuel efficiency. And maybe you've seen those on planes before if you've ever flown on a big commercial jet. They're called winglets, like it says here, or Airbus has their own term, and I think it's called sharklets. But again, it's just kind of this little upturn. I shouldn't really say it's little. They're pretty big, like 5 or 6 feet tall. So they can really kind of minimize that drag and improve fuel efficiency. All right, that does it for this video. If you have any questions, as always, be sure to ask.